Okay, so we can apply Hess's law for problems such as these. So here's our question. If you react 2 ethanes with 7 oxygen gases and 4 carbon dioxide and get 4 carbon dioxides and 6 waters, what is the heat of that reaction? What is the heat of combustion of 2 moles of propane? So you can solve problems like this by knowing from the back of your book, or most often given to you in this case with Hess's law, by knowing the heats of reactions of varieties of different reactions. If you can combine those reactions to get that overall reaction, then you can combine the delta H's of those reactions to get the delta H of the overall reactions. So we need to find a way to add up all these reactions to get that one. So what I do is I say, hey, I need 2 C2H6s on the left. And then I examine all the other reactants and products as well, trying to get them on the proper side. So first I work from the left. So 2 C2H6s, I need them, 2 of them on the left. So you'll see that I have 1 C2H6 on the right. And so I need to have 2 of those C2H6s. I'm going to multiply that overall reaction and the delta H of that reaction as well, so that I get 2 C2H6s. But I also need those C2H6s on the left. And so I'm going to flip that overall reaction as well, which will flip the sign of that delta H. And so doing all that, we should get now on the left 2 times that. We should have 2 C2H6s in gaseous form on the left. And then on the right we should have 2 times 2. We should have 4 carbons in graphite form plus 2 times 3, or 6 hydrogens in gaseous form. And the delta H, we're going to flip the sign as we flip the reaction. We should get a positive 2 times negative 84.7. We should get positive 169.4 kilojoules per mole. Now that you've arranged this equation into the one that ultimately you'll desire, you can cross out the old reaction. So now at least, when we add these reactions together, we will at least have 2 C2H6s on the left, like we need. We're also going to need 7 O2s on the left. Now, currently, you see that we do have some O2s on the left, but you'll see that it's in 2 different reactions. I want you to avoid working with compounds that are in 2 different reactions. Ultimately, they'll cancel out most of the time. So just ignore those, and eventually you'll see that they do. You do get as many as you need. So let's move on to CO2. We need 4 CO2s on the right. You see currently we have 1 CO2 on the right, so we need to multiply this whole reaction by 4 times. So that will give us now 4 carbons in graphite form plus 4 O2s in gaseous form plus 4 carbon dioxides in gaseous form as our product. And then you'll see that our new delta H, because we multiply that whole delta H by 4 as well, we should get negative 1,574 kilojoules per mole. Okay, so we've worked this equation. Let's cross that out. Next, we need 6 waters on the right. You see currently we have 1 water on the right, so we're going to multiply this reaction by 6. So we'll get 6 H2 gases combined with 6 times half, or 3 O2s gases gives 6 times 1, 6 waters in liquid form. And the delta H is going to be 6 times negative 285. It should be negative 1714.8 kilojoules per mole. Cross out the old reaction. So we've pretty much set everything up so that we have 2 C2H6s on the left, 7 O2s on the right, 4 plus 3, 7, 4 CO2s on the right, and 6 H2Os on the right. So now we should, when we add all these new reactions up, we should get the reaction that we desire. So I'll go ahead and do that. Let's see. I guess I can start from here. 4 carbons in graphite form plus 6 H2s in gaseous form plus 4 plus 7 plus 7 O2s in gaseous form plus 2 C2H6s in gaseous form gives, on the right now, 4 CO2s in gaseous form, 6 waters in liquid form, 4 carbons graphite, and 6 H2s gaseous. And then the delta H is the combination of this plus that should be, wow, negative 3,119.4 kilojoules per mole. Now let's just confirm that this bottom reaction does equal the reaction that we desire. So first let's cross out whatever we can. So I see I have 4 carbons on the left, I have 4 carbons on the right. I have 6 hydrogens on the left, I have 6 hydrogens on the right. So overall I have 2 C2H6s plus 7 O2s gives 4 CO2s and 6 waters. Perfect, that's exactly the equation I want. And therefore the delta H of that overall top reaction is negative 3,119.4 kilojoules per mole. Wonderful. Gosh, that's a long process, isn't it? If you have to do it, it does take a little while. But sometimes you get lucky, and you are given information which allows you to solve that problem. Let's derive the equation you would use with heats of formation given to you. So you saw that for that reaction, we took the heats of formation of 4 CO2s, and we took the heats of formation of 6 waters, and then we added the negative of the heats of formation of 2 C2H6s. What do I mean by heats of formation? I mean the heat to form a CO2 from its elements, or the heat to form a water from its elements in their normal stable states, or finally the heat to form a C2H6 from its elements. So this is essentially what we did. We multiplied the CO2 by 4 and the H2O by 6 and the C2H6 by 2. Actually, negative 2. So in fact, what we had then was 4, 6. We had the coefficients in the overall reaction in front of the heats of formation of the products, and then we subtracted the coefficients of the overall reaction. And we subtracted the heats of formation of the reactants. You didn't see any specific reactions for oxygen because the heat of formation of oxygen is equal to 0. But we know the heats of formation of all these other things, they were given to us in the reaction. So you see, we can kind of derive from the use of Hess's law, we can derive this lovely equation. The heat of a reaction is equal to the summation of the heats of formation of the products minus the summation of the heats of formation of the reactants. So for a reaction of, say, A turning in and B turning into C and D, and having these lowercase coefficients, we could plug in to that top equation here. Note that we have to account for the coefficients in front of the reactants and products. Now, what do I mean by standard enthalpy of formation? More specifically, at 25 degrees Celsius, the standard enthalpy of formation F is the heat to form something from its elements in their stable form. So what's the heat of formation of O2 gas? Well, to form O2 from O2 gas, because O2 is the normal standard stable form, that requires 0 kilojoules per mole. What's the heat of formation of ozone? To get ozone from O2 gas, that actually does require some heat. It's 142 kilojoules per mole. What's the heat of formation of carbon in its graphite form? Well, the normal standard form of carbon is in graphite form. So to form carbon in its graphite form involves no change, so there's no 0 kilojoules per mole for that. But what about to form diamond? Well, diamond is not the normal stable form of carbon. Graphite is. So that actually does involve some heat transfer, 1.90 kilojoules per mole. All right. Just FYI, when you are ever given heats of formation, or you're told to find them in the back of the book, you want to use these equations. Heats of formation is your keyword. You can find the values in the back of the book. Thanks for watching, guys.